So for some reason I X'd out instead of clicking on the graphs. I X'd out. Apologize about that. But we can see that case number 5 again and 135 in the QQ plot emerged as outliers and problematic. We can also see that we have a zigzag that easily goes outside and deviates from that line of best fit or from a normally distributed data set. And we can see that the standard errors which would help us make an estimate about the population, we can see that the data is actually deviating away from that in this QQ plot. Um, let's um, let's go back to one more graph. I mean, actually, let's just simply go back to the basic diagnostic graphs and let's look at the um, the residuals versus fitted graph. So the fitted line is the predicted line. This is the line of best fit in this case, and we usually want to see that this is just simply very scattered and doesn't necessarily follow a pattern. When we're looking at this graph here, we can see that there appears to be a pattern here suggesting that there might be a problem with this data. Conclusion is this a valid model? Um, no, it's not. We can further test this, and this is not necessarily a requirement, but we can further test this. Let's go ahead and conduct our statistical analyses one more time. Fit models, linear regression, and everything's already set up. Let's go ahead and click on yes. Let's go over to RStudio. Let's look at the output. Remember that we had said that age had a positive relationship and ears had a negative relationship. There's a good chance that age is soaking up the variance for ears and ears because ears and age are correlated, as we saw when we ran our correlation matrix, and then we confirmed when we ran our diagnostics, our VIF, variance inflation factor, which indicates whether a variable has an influence on another. We saw that these guys were above the generally accepted range of 1 through 10, and so they would be problematic. Let's look at what happens if we run this same analyses. Oh, let's go back and let's talk about this just one more second, one more detail. So age is positively related, but ears is negatively related. So the final test would be, what if I ran these independent from each other without them being in the same model? So let's look at age first, and then let's look at ears. Let's see if they become positively related as we would expect them to be. Let's go back to our commander. Let's run a statistics, fit models, linear regression, and let's simply select age and beauty, and ears has been clicked out of. So let's go ahead and click on OK. And let's come back to RStudio and let's look at the output. So we see that for some reason, I may have to run that again. So let's go age and beauty. Click OK. And because I'm recording this, sometimes my computer becomes saturated and I can't see exactly what it is that I'm doing. So age all of a sudden becomes positively related to salary, and it is a significant predictor of suggesting that an increase in age would have a positive increase in salary as well. So let's look at experience. In the previous model, experience was going, um, years was going in a negative fashion. Let's see what happens if I simply run a regression analysis with beauty and years instead of age. So statistics, fit models, linear regression. Let's click out of age and let's select simply beauty and years. And let's click on OK. Let's go back to RStudio and let's see what emerges here. So all of a sudden, years is also positively related to salary. In the first model, where we had both of these variables in the model, and they were both measuring the same thing because we already confirmed that we had a multicollinearity issue. We can see that as we run them independent from each other, they become significant positive predictors of salary. And that would be the end of the assignment. If you Google sagepub.com and look for the Andy Field book that we're using in class and click on the student resources, you can find further interpretation of this task. Hope this has been helpful to you.